principal component analysis. Before we start principal component analysis, just let us discuss some basics of linear algebra. So first of all, the representation of a vector is given by, a sequence of numbers in square brackets, and this is like a column vector. Okay, so the first value 1 corresponds to the first dimension, the second value the second dimension, and the third value the third dimension. Then the dot product of two vectors u and v, and you could write this as u transpose v. So when you do a dot product, the first vector has got to be a row vector and the second vector has got to be a column vector. Otherwise, if both are row vectors or both are column vectors, then the operation is not possible. Okay, so for example, 1 2 3 into 2 1 1. So here you would multiply the first entry with the first entry and then plus, and then the second entry with the second entry, and then a plus, and then a third entry with the third entry, and that would give a value of 7. And you could write 1 2 3 as column vector 1 2 3 transpose. That's possible. Now about little bit about unit vectors. So unit vectors, a unit vector for a vector v can be written as v divided by the norm of the same vector, and it could be represented as v cap. For example, for a vector v equals 1 2 3, you could write it as the unit vector would be 1 2 3 and divided by its norm, and that would be root of 1 squared plus 2 squared plus 3 squared, and that's root 14. And the magnitude of a unit vector is equal to 1, and you could check that up by computing the norm of this. So you would get root of 14 by 14, which is equal to 1. And next, a little bit about matrices. So matrices are two-dimensional, basically an array of numbers, and so addition of matrices is trivial. You add the entry in the first matrix with the corresponding entry in the second matrix. So here you would add 1 plus 2 to give 3, 2 plus 1 to give 3, and so on. 3 plus 3 equals to 6, and so on. Then scalar multiplication, which basically means that we multiply the matrix by a scalar. So the scalar simply multiplies all the entries in the matrix. So here you end up getting 3, 6, 9, 12, 15, 18, 21, 24 and 27. And matrix multiplication. So here you have two matrices. How do you multiply them? So the first entry at position 1 1. So that means that you multiply row 1 with column 1. You'd basically do a dot product. The second entry here, which is at position row 1 column 2. So that would mean that you take the first row and multiply it with the second column. And similarly, let's take this entry. So this is the second row and is the third column. So that means you would need to multiply the second row with the third column in order to get this entry. So you could just simplify the dot product of all these terms, and then you would get this matrix. And a little bit more about matrix multiplication. So matrix multiplication, it's defined for two matrices to be multiplied, the dimensions have to be compatible. So you could note here that the first matrix has dimension k into n, and the second matrix has dimension n into m. So the number of columns of the first matrix should be equal to the number of rows of the second matrix. Only then the matrix multiplication is possible. And the dimensions of the resulting matrix would be k cross m, meaning the number of rows of the first matrix and the number of columns of the second matrix. And a little bit more about matrix multiplication. You see down here some of the properties. Yeah. So matrix multiplication is not commutative, but it is commutative with respect to scalar multiplication. So if you multiply a scalar with a matrix, then the matrix multiplication with scalars is commutative. But in general, matrix multiplication is not commutative. Matrix multiplication is associative. So if you have three matrices being multiplied A, B, C, then if you multiply AB first or BC first, it does not matter. You get the same result. And something about transpose of a matrix. So you see here that there's a matrix given, and this is the transpose, meaning the rows of the first matrix become the columns, and the columns of the first matrix become the rows. Or if you want to write it in another way, you can say entry Aij here becomes the entry Ji here. Okay, the entry Ij here becomes entry Ji here. And some properties of the transpose. So A transpose, the whole transpose, the same as A, and AB transpose, the whole transpose is B transpose A transpose. Next, the projection of a vector in the direction of u. So projection of a vector v in the direction of u, what does it mean? So if you look at this figure down here, the projection of u1 along u2, and that's just, I drop a perpendicular from u1 to u2, and this length here is the projection of u1 on u2, and it can be computed as u1 transpose u2, basically a dot product between u1 and the unit vector of u2. And you can just easily known, to many of you it would be known, that this is the same as u1, the magnitude of u1 cos theta. Okay, so note that dot products are always scalars, right? So u1 transpose u2 is a scalar. and just an example here of how you would compute the transpose. If you have a vector v and a vector u, then v transpose u, the first one is a row vector, the second one's got to be a column vector, and u cap is computed by dividing u by its norm, right? So then just expand. Next, it's especially in principal component analysis, it would be useful for us to determine what are the eigenvalues and eigenvectors of a matrix. So if you have, for example, a matrix 2, 3, 3, 2, and you want to find out its eigenvalues and eigenvectors, then you would do it by definition. The definition of eigenvector is that if you have a matrix A, then A into AB is equal to lambda V, and that's the definition of an eigenvector, and lambda is the eigenvalue. So anyway, so V, I've just written the dimensions of V here, V1, V2, and this means if this holds, then I can write this by rearranging the terms in this way. Okay, so then I would get 2 minus lambda 3, 3, 2 minus lambda into V1, V2 equals to 0. And you know that this system has infinitely many solutions. Okay, so it follows that for a system to have infinitely many solutions, meaning the system is indeterminate, then the determinant of this matrix has got to be 0. Okay, and when you equate that to 0, you get an equation of this form: lambda squared minus 4 lambda minus 5 equal to 0, and that means that lambda is equal to 5 or lambda equals to minus 1. So now we substitute these values back in equation 1, and when we substitute lambdas back in equation 1, we get the relationship between V1 and V2. So for example, for lambda equal to 5, we get V1 equals to V2. Okay, and for lambda equals to minus 1, we get V1 equals to minus V2, which means that the eigenvector is V1 V1 or V1 comma minus V2. Okay, so V1 is just a scalar. It could be removed out of the eigenvector. So for example, for example, a vector like V1 comma minus V1 could be written as V1 times 1 comma minus 1. So we would just say that the eigenvector is 1 comma minus 1. You could as well say it's V1, anything multiplied by 1 comma minus 1 is also an eigenvector, right? But that's just it's trivial to realize that. So if we have an eigenvector, then if you multiply the eigenvector by a scalar, then that's also an eigenvector. But anyway, we have expressed in the simplest form. So the eigenvector could be 1, 1, or it could be 1 minus 1 or minus 1, 1. Okay, so these are the eigenvectors. But in the case of a covariance matrix, you would normally find that the eigenvectors are positive. Not normally, always the eigenvectors are positive for a covariance matrix. So this is the end of this clip on basics of linear algebra.